I hope you all are well. So today I would like us to look at another problem, but this time around it is a problem on center of gravity. So look at the problem. We are told that we need to locate the center of mass, and in bracket we have x bar, y bar, and z bar of a homogeneous material. So the first thing you must know, what is a homogeneous material? It's a material that has the same, it's a material that is having the same material composite. So the material is the same. The same throughout the design. So this is having material which is made up of different sizes, different shape. You could see this is actually a rectangle, this is a triangle, and this is a rectangle. So homogeneous means the material is the same throughout. And therefore we have to locate the center of gravity for x bar, y bar, and z bar. So now what is the first thing you have to do? The first thing you have to do is to be able to write out a simple formula. And before we write out a simple formula, I'll break this into different parts. I can call this part 1. I can call this, that's a rectangle, I call it rectangle 1. I can call this rectangle 2 if I choose to, and I call this triangle part 3. So I have part 1, part 2, part 3. So I have 3 different shapes. Now I may decide to write this formula for x bar, which is, because it's a 3D problem, it has z, it has x, it has y. I can talk about a volume because volume is 3 dimension, while area is 2 dimension, and it therefore means I can write the formula for x bar, which is the center of mass for x axis, which will become what? The sum of x bar times the volume over the sum of volume. So this is the summation. So this is the sign of summation of x bar and v bar for part 1, part 2, and part 3. And I have part 1, part 3, and part 2. So those are the summation of the x bar multiplied by the volume. So it's the total. So it is the total. So it is the total of x bar multiplied by the volume for part 1, part 2, part 3. And this is the total, or you call it the summation of the volume for part 1, for part 2, and for part 3. So but now let's see how this formula is being applicable. And here I gave you a picture which I would like us to use for the centroid. This is actually the centroid we're talking about. That is the centroid. And it depends on the shape. Every shape has its own centroid. For rectangle, this is at the different centroid. For the different axes for x and y. I'll talk about that. But now let us see how this formula is being used to solve this problem. However, in an exam, I'll give you this formula, but I will expect you to get the respective center of gravity and the volume for part 1, part 2, and part 3. Now let's see how that is achieved. Let's see how that is achieved. X bar is equal to what? The sum of x bar and volume over the sum of the volume is equal to what? Now I will start with part 1. And this is my part 1. So my part 1 is my rectangle. That's my part 1. So because I would like you to see clearly, then let me clean this properly so you can see the dimension carefully. So let us look at the x direction. So this is the x direction for part 1. Let me highlight part 1. This is part 1. It's a rectangle. It's a rectangle. So the first thing you have to look at, this is the rectangle. From this side to this side is actually 150. Is 150 millimeter. And therefore, what is x bar? X bar is equal to what? 150 divided by 2. And therefore, x bar is equal to 75 for this rectangle. That is, the x bar lies in this center. So it lies in this center. So it lies at the center, which is actually this distance, which is 150 divided by 2, which is 75, and therefore I'll have for part 1, I'll have 75 is my x bar. And what is the volume? Remember, volume for a rectangle is length times width times height. And of course, and I have a volume, I have this section, that section, that section, and that section. That's the volume. So if you cut this piece, that's the volume. So effectively, I have 150, which is this side. So I have, or if you want to start with the longer side, I'll have 200 plus 250, which is 450, plus 100, and that will be 550. So if you want to start with the longer side, you have a length of what? Of 550. You have a length of what? 550. And what is the, remember, volume is equal to a length times width times height. What is the width? The width is 150 times 150. And what is the height? Is still 150. Is 150. So this is 150 and this is 550, and that is the volume. That is for part 1. And I have plus what? Plus, I'm moving out to what? I'm moving out to part 2. And my part 2 is, I want you to see part 2 properly. So my part 2 is this guy, and this guy is also a rectangle. That is my part 2. But now, interestingly, for that part 2, we are going to get x bar, and therefore the x bar is measured from this reference side, which is actually from the intersection where I know I have z, I have x, I have y. So we always measure the reference from this intersection point. From this intersection point. That's where we measure the reference. And therefore, I have this to this, which is actually 150. If I clean this, you will see I have from the reference, which is actually from this to there is 150. So I have 150 plus, then now I have this from here to here is actually the x bar will be 150 divided by 2. X bar will be 150 divided by 2, and therefore I'm going to have x bar for part 2 is going to be 225. It's going to be 225. That is x bar. So technically, I have piece 2 or part 2. I have 225 is the x bar. And now for the volume is T, length times width times height. And if you go to that piece, you can see if I talk about my length, I'm dealing with this piece. Remember, I'm dealing with this piece. I'm dealing with this section only. This section. So technically, I'm dealing with a side of what? A side of 200. So if I say my length is 200, and my width becomes what? My width becomes, this is the width, which is actually 150. I'll have 150. So I have 200 times 150, and I have the height. The height is equally 150. It's equally 150. That is this height. It's equally times 150. And plus, I move to my last part, which is part 3. And part 3 is a triangle. And the triangle is actually from here to here. I have this is the triangle. So let me try to project the triangle so you can see. The triangle starts from here, and that's the triangle. So technically for triangle, if I am going to measure the height or the eccentric along this z-axis, it becomes along this height section. But because I'm measuring from the base, from the base to this point which I have that x bar, I'll use h over 3. I'll use height over 3. If you are measuring from the top, then it will be 2/3 the height. But if you are measuring from the bottom, so you have to take note, if you are measuring from the bottom, it will be h over 3. So the centroid from the bottom is h over 3. And technically, how do I measure that? I have x for part 3. I have h over 3. And I have a part which has a point from a reference. So I have this rectangular piece, which is a distance of what? It has a distance of 150 from the reference point. So I'll add plus 150. Therefore, this height is equal to what? What is the height? The height is 150. The height is actually 150. So technically, x is equal to what? 150 over 3 plus 150. And therefore, 150 divided by 3, I'll have 50. Plus 150, I'll have 200. Therefore, I'll have 200 for the x bar is 200 for part 3. And what is the volume? The volume for a triangle, the volume for a triangle is equal to what? Volume for a triangle is equal to what? 1/2 base times height times length. That is the volume for a triangle. So the volume for a triangle is half base times height times length. So I'll write the volume, because this centroid x bar times the volume. So the volume for part 3, which is a triangle, is half base. And now what is my base? My base for that triangle is 150. So my base for the triangle is 150. And what is my height? The height is 150. This is the height, 150. And what is the length? The length is this side, which is 100. The length is 100. And that is how I get my x bar and the volume for the respective parts from the reference point. And where is the reference point? This point of intersection is always the reference point. So we measure all our centroid from the reference point, and every shape has a unique way on how to measure the centroid for x, y, and z. But we are still looking at x axis. And all this should be divided by what? The summation of the volume for part 1, for part 2, for part 3. So the sum of volume of part 1 plus the sum of volume for part 2 plus the sum of volume for part 3. And now we would have the volume for part 1, for part